Hi everyone. So welcome to this video. This video is actually about force balance in unidirectional flows. And what I wanted to do here was give you an example of something that we will discuss in class. And this will essentially design so that you can also get some input for homework 3, problem 4, and the last part. And the reason I wanted to do this separately than the lecture was that sometimes this can take a little bit of while to discuss, and I didn't want to rush the discussion in class. Um, and hopefully this will also give you some practice for your homework problem, but in general also conceptually, I think this is an important concept which needs to be discussed a bit slowly. So I wanted to make a separate video for that you can watch whenever you have time. So let's basically discuss what we have discussed in class. Essentially is that uh, is this unidirectional flow system when there was a at x is equal to 0, x is equal to L. Pressure here was P is equal to P1. Air pressure was P is equal to P2. We said delta P is P2 minus P1, right? And that we basically found that the velocity profile is parabolic, or the Poiseuille flow. This is the simplest unidirectional steady state, fully developed system. And this is what we have discussed in class. And what we found was that the velocity is only in x direction and vx is dependent on y. And the formula looks something like this: 1 minus 2 mu delta p by L h square into 1 minus y by h whole square. Okay. So this is the formula that we have discussed and we have derived in class, and this is the parabolic profile. Okay. So now that we have discussed this, I hope you can imagine that if the plates are kind of, are at rest, then if the fluid is moving, the fluid is actually trying to drag the plate with it, right? And so that it is applying force on the plates, and of course the plate is applying the equal and opposite reaction on the fluid. So typically, basically, we have discussed about stresses. We have also discussed about forces in a hydrostatic system. But what I wanted to do was that I wanted to do a force calculation on a system with flow. So in hydrostatics, we have done that, but we have not done that with flow. So the goal here is to actually construct a control volume like this, which basically goes throughout the system. And note that basically go back to the equations that we have discussed in class that, and I will just basically mention that this in class we said that this term actually completely drops out. The left hand side term completely drops out is minus grad P plus mu del square V. Okay. This term completely drops out. So it means that the fluid is basically does not have a rate of change of momentum, or the net force on the fluid or by the fluid is essentially zero. So what we want to do is, let's say the force uh, on this surface is F top, right, F bottom, F right, and F left. So I hope first it makes sense why we are saying the force is zero, because the velocity it's steady state and the v dot del v is exactly zero. We showed this in the class. The left hand side completely drops out and the pressure is balanced by the shear stress, is essentially meaning it's in other words, in an integral balance, this means that F top plus F bottom plus F left plus F right is exactly equal to zero. And we need to have, it has to follow. This has to be true. It cannot be not true. Okay. And what I'm basically doing here is the force by the fluid. You can basically do the opposite and say force on the fluid on all these four faces has to be zero. It's the same because everything will become just a negative sign. So this is the idea behind the video. And I will basically go through all the four elements. And the main thing here is whenever we calculate force, we go through a stress vector as we have discussed. So let's start with the top, F top. Okay. So F top would be something like, I will call this as S top, okay? And so this is the stress vector, okay? And the main important point here is, and this S, I will write this for general, not just for top, is that we know that S of n is n dot sigma, and sigma is nothing but n dot minus p del plus tau here, right? And this matrix here, in this case, is actually 2 by 2 matrix because it's only two-dimensional, x and y, right? There's only x and y. We are not talking about a z dimension. So basically, we can write this as minus p0, 0 minus p, okay? And forget the n for right now, just write n dot plus, and this is crucial, this is something we have not discussed till now in this form before. We have been writing this as the approximation, right? Transpose, right? I'm now writing this in an actual tensorial form. It will become like this, and you can check this yourself. Basically, you get a symmetric matrix with the diagonals being twice of del vx by del x, del y by del y, it's twice. And the diagonal terms basically become the opposite. Del vx by del y plus mu del vy by del x. Okay. So please make sure that you're able to follow this matrix here, 2 by 2 matrix, because it's only x and y. And the point here is that vy is 0, vy is 0, and vx is only a function of y, right? So this term goes away. Why? Because vx is only a function of y. This term goes away because it's only vy is 0. Then vy is also 0, vy is 0, and vx is a function of y. In simple terms, basically, this is how our stress tensor becomes minus p mu del vx by del y, mu del vx by del y, and minus p. So this, and similarly, we'll just move this here. Vx is a function of y, and vy is 0, which is used to cancel out these terms. Okay, so this will be our stress vector for all the surfaces. Depending on what surface we apply, what n dot we apply, this is what will happen. And I hope this also physically makes sense of why we are getting the stress vector, because the pressure always acts normal, as we have discussed several times over, but the shear stress can only happen because of the velocity in the x direction and the gradients in the y direction. So the velocity is only dependent on y. So that's why it is basically, the shear stress is Vx, del Vx by del y, because that's the only direction it is changing. And it always will act tangentially, so that's why it is off diagonal component. Okay. Now, I hope this is clear. So now what I will do is I'll find this on S top, okay, which is basically the surface on the top. And the surface on the top has a normal going into the fluid is always this. So N is minus EY, okay, N is minus EY. So let's go with S top. S top is of minus EY, or this becomes 0 comma minus 1 into minus P mu del Vx by del Y, mu del Vx by del Y plus and minus P, okay? And please, this is a good habit to learn how to multiply these matrices. First, you take, piecewise multiplications of these, add them, and then take the second, similarly do that for the second term, and you'll get a 2 by 2 matrix. And this will be minus del Vx by del Y and plus P in the second term, or minus del Vx by del Y Ex plus PEY. And I again hope this makes sense that the shear stress is actually pushing the plate in the x direction, or dragging the plate in the x direction or by the fluid, and the fluid is pushing the plate in the positive EY direction on top, right? It's pushing positive direction on top. And now we already know what Vx is. So we know Vx, what is Vx, right? And del Vx by del Y, or rather mu del Vx by del Y, is what? We can find that out. The mu del V x by del y is delta P by L, uh, and what you will get is delta P by L into Y. Basically, this is what you will get. You can verify this, that this is mu d del V x by del Y, and at y equal to h, this becomes delta p by LH. Okay, just let me make sure that there is no negative sign. Yeah, this is correct. So this becomes delta p by L h at y equal to h. So just make sure you can check this to differentiate, and you get this differentiate. Okay, so this becomes delta p by L, or this becomes minus delta p by L into y, and y here is y equal to h. So yeah, y equal to h, px plus pey, or finally we get minus delta p by L into h px plus pey. And this is s top, which is in the minus e direction. Okay. So we get this out here, and now note that depending on which location you choose, so the plate is extending in the x direction, right? Now the pressure is actually varying in the x direction, like we had discussed in class. Pressure is linear, so the pressure is changing in the x direction. Therefore, we cannot simply integrate, just say, oh well, you can integrate this. This is not constant essentially. That's what I'm trying to say. That s top actually varies, but what will happen is because there is also a bottom plate, it actually does get cancelled out. So I'll come to that. The second thing is, note that we are getting a minus ex sign, but also note that delta p is actually negative because the flow is happening from left to right. So we had discussed in this class, in the class, that delta p is negative. So that's why it's actually in the positive ex direction, which physically makes sense that the fluid is dragging the plate in the positive ex direction with it. Okay, so I hope this also is physically intuitive. So what I will do is, now I will also write as bottom. So essentially, rather than doing it twice because of the symmetry, I'll also write as bottom with plus ey. Okay, it will become something like 0 1 into minus p mu del v x by del y, mu del v x by del y minus p. And what you will essentially get here is mu del v x by del y, and please verify this. This should not be too difficult to do. Minus p e y. Okay, and this is happening at y equal to minus h now. So if I substitute the value in this formula here, minus h, I get again a negative sign, or minus delta p h by h by lex minus p e y. Okay. So as bottom. So we also get this as bottom here. Okay, and note that this is equal, and in the x direction it is equal, but in the y direction they are opposite. Basically, the pressure force is opposite, whereas the tangential force is in the same direction, which kind of makes sense because uh, the shear stress is actually should be the same on the bottom and the top plate because it's symmetric flow. So that's why they do come out to be the same in the x direction. And again, we have just automatically used the formula, and the directions all come out to be consistent. Okay. And the reason I did this and did not directly calculate the force is because now our S top and S bottom become a bit easier, and because the dA is, it's the same geometry, so the dA will remain the same. So F bottom plus F top essentially could be S bottom plus S top dA. Okay. And what you will get out here is minus 2h into delta p by L dA, integration. Okay, and note that this is constant, so I've taken this out, and the area of this plate is L times W. So let's say that the width of the plate is sort of W here. Okay, let's just assume that's the case. So then we will get basically minus 2h, and there is an ex here, so I should not forget that. Minus 2 times delta p into H times W Ex. Okay, so this is what I get for F bottom plus F top. Okay. So I hope this is, this is sort of, you can see how we do these problems when there is flow plus pressure. And again, I would like to stress out that this is sometimes students don't appreciate this, that there is a pressure force in the y direction. It just is getting cancelled because they're asymmetric. But the plate at the top is actually experiencing a pressure force which varies along the x direction, because as you can see, pressure is changing along the x direction. And so it is actually, the plate is experiencing a varying pressure force for different x, but it just gets cancelled in the overall balance because it's symmetric in top and bottom. Whereas the shear stress actually adds, they basically add together. Now what we will do is, so we have done a bottom and top. So the bottom and top we have done here, n was Ey. I hope this was clear when we were discussing. Now we'll go to the left and the right one. Okay. So the left one, the n is minus Ex, sorry, plus Ex, and the right is n is minus Ex. Okay. So let's go to the left one, which is F left. Sign S left is actually plus Ex. Just to clarify again, S left is plus Ex, so the normal is within the fluid, so plus Ex, or this becomes 1, 0, and again minus P mu del Vx by del Y, mu del Vx by del Y, and then minus P, and what essentially you will get out is minus Pex plus mu del Vx by del Y, Ey. And now note that I cannot really, I know that mu del Vx by del Y is actually a function of Y, right? It's clearly a function of Y. So this right hand side, this term is not constant now anymore. Now the opposite has happened. The pressure is constant because pressure does not vary along the Y direction. And this left phase here is varying along the Y direction. This phase here, Y varies along this direction. So I cannot calculate this, or this is delta P by L into Y, right? So this is varying, but then as usual on the right hand side, it will be the opposite. So it does get cancelled out. Sorry, that's right. Or minus 1 into 0 minus P mu del Vx by del Y mu del Vx by del Y minus P. And then what you will get out here is Pex or plus Pex, right? Uh, and then you will get a minus mu del Vx by del Y Ey, or you get Pex minus delta P by L Y Ey. Okay. So now when you do S left left plus S right, and note that this pressure here is P2, this pressure here is P1. So what you will get is P2 minus P1 into Ex, which is equal to delta P into Ex, because these two terms, when you add them, this will get cancelled by this term when adding, right? When you add them, these two terms will get cancelled out. Or finally, F left plus F right is delta P into Ex times dA, and again this is constant, so delta P Ex comes out constant, and dA, and this dA is simply area, which is 2H into W. So I'll discuss why that is. I hope that is clear though, that this is 2H into W. So this is the plate this is the face we are talking about, 2H into W, and the same area here. So the same area here, 2H into W. or we get this as, so then F left, so I'll just make it sum of F i's, is 0 because this is 2HW delta P and this was minus 2HW delta P. So basically, this can show you a force balance that comes out clearly from our velocity profile. So let me just quickly recap this, and I again hope this was helpful. And you do a very similar problem in homework 3, problem 4. But it's very important to understand this how to do force balance, a vector-based force balance from stresses using velocity and pressure. So we had the velocity profile, okay, and then we said that there is no acceleration or there is no rate of change of momentum on the left hand side because steady state and the nature of the system. So there's only the force balance is zero. Basically, the external force, the surface forces have to balance each other out. So in an integral sense, the surface balance at the top, surface balance on the left and right, and the bottom have to balance each other out. Here I am calculating surface forces by the fluid. You can also calculate forces on the fluid. Okay. So then I start with F top. To calculate surface on the top, you take the normal into the fluid, which is minus EY. Uh, but sorry, before that, to calculate stress vector, we basically said, okay, this is the way our matrices will look like for pressure and for shear stress. In shear stress, the only components that will be the off diagonal components, which will be mu del bx by del y. And so we added them and got the stress vector. Then we did the top stress vector by using a minus EY, and we got a value where we saw that there was a constant EX, but the pressure was varying along the X direction. But because of the bottom surface, which was the equal and opposite in the Y direction, we could cancel that out. But the shear stress actually does get added. When you add them, you get a value. Similarly, we did the same exercise of n dot sigma with 1 0 and minus 1 0 for left and right. And again, you saw that when you add them, essentially you get cancelled out the shear stress. Now the pressure forces get contribute, and at the end of the day, both of them result in identical results. Or basically the sum of the forces ends up being zero. So I hope this was helpful. Uh, I feel free to write to me if you have questions. But I hope you feel comfortable with now how to use stress vectors to calculate forces and how to combine pressure forces and shear stress forces. All right, so I'll see you in the next video and look forward to getting your questions. Bye bye.